this stores the parameters, but it doesn't store the results or the, let's say, the important values of the program runs, but they are stored in the log file. So one of the strengths of OPALS, just to put it short, is that there's a strict logging, and everything which is logged is not lost, but is preserved here in this XML type. Logging, as you see, you have the full list of parameters. As you see it here, we only specified one of the parameters. All the others have been either estimated, or there had been an internal default, something like that, so you always know what the program does. For instance, we use the tile point count, whatever the tile point count is, forget it, but it was an internal default to 200,000, and it is protocoled in here, so you'll find all the parameters which were used for your actual program run in the log file. Okay, so now the QGIS show that, well, not so nice probably representation of your data, so we might want to generate, and I go back to my shell, to my OPALS shell in here. We might want to have either a shaded view or a color, a colored representation of our data. So let's first run the shader. We don't use GDAL, what is it? DM?
DM.
DM.
Yeah.
But we have an own module for this, which is called shade. So just type shade minus in file. In this case, the input is the raster file. So it should be sb-large underline set.tif. Leave all the rest again to the program to estimate the parameters like the illumination direction, the method, the shading method, and things like that. And actually, it produces a file called sb underline set underline sht for shading. Again, .tif. We also use the GDAL library, so whatever GDAL is able to produce, we are able to produce. So if you use the plugin from the Kia, we would also be able to produce Kia files. And before we have a look at it in the QGIS, we simply run the colorizer, which is set color. Sorry for the American spelling to all the British in the room. It's just shorter. And again, same story. Just supply the name of our input raster, which is sb-large underline set.tif, and we leave the rest again to the program. Ha! This is a very good thing to show. If you have successfully run this command, then you should find in your Windows Explorer a file with the ending underline setco.tif. If you just double click it, then we just visualize it in a image viewer. And what we see here is we have a nice color-coded representation from green to yellow. Probably you would rather like to have the entire range which, from the color palette, which is going from green to brown. And why didn't we get brown color tones? We see it here from the logging that we have one isolated outlier in the elevation in the range of 320 meters. Then we have quite nothing till 275 meters, and again nothing till 260 meters. So apparently our actual set range is between, what is the first one? Between 180 and 260. How would we do this? How would we deal with that? And there is one thing coming into play which is really worth mentioning. We have this ODM, and the ODM gives us geometry on the one hand side and attributes on the other hand side. And one thing of which the framework is offering us is a very generic filter. So we can access all the information which is stored in the ODM, and we can subselect the data, be it geometrically or in terms of attributes, by a specific filter string, right? In this case, we probably want to create our DEM only in the proper set range. How would we do this? We would run a filter, so we would rerun the grid command. So probably you can use the arrow keys to go back to your grid command. So in order to save typing, right? We should end up with something like that. And then we specify the filter, which is minus filter. This will be a complex one, so we need to quote it, double quotes. And we would use a generic filter. So this is the keyword generic, and then in brackets we would simply use all the set values, and we can address it simply by set lower than, what was the upper bound? 260? I think it was 260, yes? 260. Okay? What would be the reaction of the program? So the gridder would try to interpolate the model using all the points, no, not all the points, but only those points with a set lower than 260. Right? What did I do wrong? Ah, okay. Again, this is probably a good thing that it happened. I have the grid file open in QGIS. QGIS is a really a nice application, but there's one, let's say, drawback on it. If you have something open, it has a handle on the file, so you're not able to rewrite it. So what we basically have to do is to close the data set in QGIS if you have it open as I have it. And if your QGIS installation is in German as mine, then this would be entfernen. Alright? Click OK, then it is gone. And now our command should work. And what we see now here, the statistics of the output raster file is that it is in the proper set range between 180 and 260 meters. And if we now rerun our set coding, again use the arrow keys to go back to your set color command, you would see that we don't have this, let's say, outlier classes, or however you want to call them. We can even here specify a specific set interval. Where's my set color? Here it is. By specifying minus into, let's say, 1 meter height bands, one color for 1 meter range. This gives us a smaller range in here, right? And if we would now visualize it either in QGIS or in an image viewer, we would have the entire, let's say, color range represented in our.
What was the last one?
Yeah.
Okay, I was too fast. The last command was the same set color which we had beforehand, and I simply choose a user-defined interval. So this is an abbreviation of interval. It should be like that. Where I'm. Interval 1 meter. Oh. Okay? This was the command. Right? So, so far so good. We have a point cloud. We've visualized the point cloud. We have queried information from the point cloud. We have rastered our data. We did visualizations of the rasters. Next thing is we would like to have a look at full waveform attributes. Why not having a look at full waveform attributes? So in order to save you from typing, we have prepared scripts. So please go back to your Windows Explorer. No, sorry. Go back to your workshop shell. Where is my workshop shell? It's the green one. In here. You find a Notepad++ text editor. It's 6. Choose 6, and this should open up the Notepad editor, right? Go back to your Windows Explorer if you're done with opening the notepad, and you should find in your directory file called underline. Well, I order it to by names. And then you find it in the top part of the window, and this is fwf attributes dot for batch script. Just open it. Not double click it, but drag it in here. In blue you see here, in black you see the commands. In blue you see the commands which we want to execute. And the first one is again an OPALS import command on the same. Am I too fast? Should we wait? Pardon? Okay. Yeah. In the meantime, I can explain the comments. As you see here, this is a simple batch file. So whatever is a comment for a batch file, in this case the REM. You can also use the double colon as a comment sign. Everything which begins with an REM is a comment and will not be executed because it is only a comment. And the first row tells us what we want to do. We want to visualize and analysis full waveform attributes, right? So where are our full waveform attributes? Actually, they are stored in the last file, but we didn't see them beforehand because they are stored as extra bytes. And by providing the proper format specification, which is provided in this XML file, we can read in all the extra bytes, right? So what we here do is we import this very same data file with a different, let's say, format specification, which basically means last 1.4 underline 2, which basically means point record format 2, with additional extra bytes. Let's have a look at this at this format specification. So what would I do? I would close this one and I would go back to my Windows Explorer, and you don't have to do it on yourself. I just demonstrated. This is a format definition in an XML file, just as we had it in Pete's presentation with the calculator. I think calculator is a term. Yeah. So this is, let's say, a generic description of what the contents of the file is and what we expect to import. And in this case, we have last 1.4 version format 1.4 point record format 2, and we want to additionally import the echo width attribute, right? So our last file contains echo width. This is not part of the last standard, but it is in the file as an additional attribute, and we just read it into the ODM by specifying that we want to read it in this case, right? So, having said that, we go back to our shell. No, we go back to the editor and just close this one. Go back to our batch file and copy this line. Control C, or however your copying strategy is. Go back to the OPALS shell. Clear your command line. Right click, and then it should be imported. Yes? Basically it tells us that it has found an echo width attribute in here, and I won't comment the rest of it. What we now can do is we can rerun the info. We should have it in our buffer. So just use the arrow keys to go to your info command. This was it. Which, as I told you, gives us all the statistics about the file, and we should now find an attribute called underline echo width. In this case, this was the name under which we imported it, and the value ranges from 0 to 38, in this case nanoseconds, with a mean value of 4 dot whatsoever and a standard deviation of 0.8. Right? So, what can we do with this now? First, we would now be able to do the same thing which we did beforehand with the set value, also with these attributes, with any attributes. So we would be able to rasterize the echo width. Yeah? But we've already done this, so we can skip this. What we now want to do is, we want to do a statistics. We want to derive a histogram. So there is a histo module, and in this case, what are we doing? We are using the sb.odm. I think this was probably part of our, this was the output. In this case, we specified the output file just a bit shorter. So it's sb.odm in this case. Specify this as input, and we want to analyze the attribute amplitude with a bin width of 10 digital numbers in this case, and the sample range should be between 0 and 150. So just let's do it, copy the line. Control C and execute it. So it analyzes the, in this case, the point cloud. It goes through the point cloud. Yes.
What does this call stand for?
What does
the call? I mean the first.
Well, it's just a matter of the syntax of the batch file.
Okay.
If you ran it as a file rather than running it, copy and pasting it as a command line.
But because the first line did not have the call. I mean,
yeah, well, it is not very strict about. From the operating system side of view, there are tiny little differences if you call a sub-process or if you just write the command, which in this case would in both ways work, as you see it here. Right? Little bit of consistency in this, but this is of minor importance for us. If we go back to the Windows Explorer and again order it by date modified, then we would see here well, first we see the log file. Let's double click on the log file. And it always starts at the last run. No, it starts at the first run. We have to go to the last run, which is the histo in here. And this is a nice representation now of the results in a tabular way. I'd just like to make the file the window larger, but I'm not successful in doing so. But anyway. What we see here is at the very bottom. Yes, this is it. This is our, let's say, the results of our histogram. So we have a minimum value, in this case amplitude of 300. We have a maximum value of 350. Please keep in mind that we did only the sample range between 0 and 150. So everything beyond 150 went into the overflow bin with a mean value and a median value, standard, well, yeah, all these, let's say, standard statistics. That's probably a bit boring, so we would probably have rather a proper visualization. In this case, a scalable vector file, scalable vector graphics file is produced. So double clicking on the scalable vector graphics file would show you the histogram, the distribution of our amplitudes, and on the y-axis we have the density of the amplitude in percent. Yes. Like that? Yeah. So we can also do, let's say, standard statistics with OPALS. That's what this is basically about. And let's now switch back to our.
I think what we need to stop the three computers at least being worked out.
So probably all the others may want to derive a histogram of the echo width. So try to figure out how you would create a histogram of the echo width attribute, right? You have the templates from the amplitude, so it's quite easy to do. Right? In the meantime,